Hello, in this video I'm going to talk to you about AC induction motors. So let me begin by talking about the references that I used for this video. First reference, which is probably the one I base most of this video on, especially the equations and stuff, is Electric Machinery, 3rd edition. Now there's some later editions, and I can only assume they're going to be even better than this. This is a really good one. It is very theoretical, but also it helps you go from theory to practice with lots of good examples. The other book that I use is the one that I used in engineering school, and this is quite good, but it tends to be more theoretical and a little bit more difficult to apply to practical situations. All right. On the internet, there's quite a few articles and websites there. They're very helpful, but let me point out a couple of them because I use some of the material from each one of these. The first one here is the 3-phase induction motor construction from Electrical Academia, or actually from Home Induction Motor 3-phase construction. And here has a good blowout, which I use in my presentation. Good construction detail, really good article here on induction motors. The next one is really good. I really didn't talk much about failures here. I was talking more about how it works and the modeling. But wow, isn't that pretty? Really good stator winding here. This is one that's what it's supposed to look. And you can see that what you've got is you got like slots here. And so the winding goes around. And so your phases are kind of distributed around the stator here. And this is what generates the magnetic field. And here it goes on and shows you some faults that you can have in stator windings. Very good pictures. I think quite good article. The next one is Basel, and this right here is mainly about DC motors. Here you see what you have is you have your stator windings and you have a magnet for the rotor here. And so we're talking about an AC induction motor which has windings in the stator also, but what you have is you have a squirrel cage type rotor in the center. But I like this, and even though these are salient poles as opposed to a smooth air gap type winding distribution, it makes it a little bit easier to understand the concept of poles. And here you see that there's always at least 2 poles, and they come in pairs. Okay, and so here what you have is you have phase A, phase B, and phase C. Okay. That's a 2-pole. Here's a 4-pole. You notice you got 4 poles for phase A and so on. And here's a 6-pole. We got 6 poles for each. And it shows the winding. So here again, this is a really good article from Basel Networks. And then the last one here, for some reason, this kind of is not showing up very well. I'm not sure why. Seems like when I first looked at it, it was okay, but this is really good because it talks about the difference between the squirrel cage and slip ring induction motor. Now I'm talking only about the squirrel cage, but there are situations where a slip ring where you can access the stator, the rotor, and actually put resistance in it to get different characteristics and stuff. Okay, but we're only dealing with a squirrel cage rotor. There's no slip rings, which is one of the advantages of this. Okay. But it goes through and it's actually got some good pictures. Here's a good picture of the rotor. Another good picture rotor. Here's one with slip rings, okay? And this is one with a wound rotor as opposed to a squirrel cage. And then here it actually goes in and gives you a good comparison here between the squirrel cage and slip ring. Another good website. Okay, let me go on and let's see this. I think I can get rid of this. Okay, close on. Okay, and my computer's kind of a little sluggish here for some reason. Okay, and all right, let's go in and let's look at some pictures. Okay, you probably recognize these pictures here and this too. Put all these together to kind of come up with a really good picture here to explain what's going on here. So here's your induction motor. Key parts is you have your stator winding or stator coils. Here you have your rotor, which is a squirrel cage type rotor. And essentially, and here's an expanded view here of the rotor, a colored picture. And notice how this is a smooth air gap, not salient pole like I saw for the DC motors. But see how the windings are kind of overlapped, you know, over here. Now what happens is when voltage is applied through the wiring box into the stator coils, it generates, and we're talking about a three-phase motor here, it basically goes in and generates a rotating magnetic field. Okay, and this rotating magnetic field induces currents into the rotor. Now the rotor has these loops here. There's a shorting bar here and these rods here that conduct, and what happens is currents are induced in these rods and it generates a field. And also there's resistance here like there is in all conductors. So what happens is basically this field here induces a field in here which induces current. This current in turn generates a field which interacts with this field and it tends to rotate. Okay, now this will never rotate as fast as this field. The speed at which the field rotates is called the synchronous speed. Okay, but anyway, this is the basics of what's happening here. And notice that this is without the magnetic material inside here, and these are laminated together to minimize eddy current losses in here. But basically you have these current loops here which generate the field in here. Okay, so that's your basic induction motor, and I'm going to show you a model that models this plus the interaction of this in the magnetic field generates changes to the parameters inside the model for this. Okay, here again we see the pictures that we saw in one of the other sources. I went in and got rid of this. Those were DC motors where you had a magnet on here, but here what we have for the induction motors, we have basically a stator which has a bunch of coils, and there again the ones for the induction motor are actually distributed windings. It's a smooth air gap. You don't have big breaks like this. Okay, these are salient pole type construction. But the reason I'm using this is because it's much easier to see the different poles with this type of construction as opposed to the smooth air gap. But anyway, this is a two pole and this is three-phase. So what we have is we have 2 poles for phase A, 2 poles for phase B, 2 poles for phase C. And so that's a 2-pole. We have a 4-pole. You've got 1, 2, 3, 4 poles for phase A, 4 for C, and 4 for B. And you have 6 poles here for phase A, B, and C. Now, the reason this poles is of importance here is the more poles you have, the slower the rotor moves. Let's look at these formulas here. W here is the actual synchronous speed of the magnetic field that's rotating here. Okay, this is the magnetic field's moving around at a certain speed. The rotor is pulled by that field. Okay, kind of like the tides or something trying to pull you out in the ocean. But just like the tide's trying to pull you out in the ocean, there's some slippage, right? The waves go out or the undertow goes out, but you kind of resist. Well, that's what this is doing. Okay, and so what happens is the speed of the rotor is not going to be going exactly the same speed. It's going to be slower, maybe 2% or whatever, slower than the actual speed of the synchronous speed of the magnetic field. Now the synchronous speed of the magnetic field can be found through W, and this is in radians per second, is 4 pi times the frequency of the AC voltage that's coming in. Now here in America, we're talking about 60 hertz, okay? So 4 pi times 60 hertz divided by the number of poles. If it's 2 poles, you divide it by 2. If it's 4, you divide by 4, 6 by 6. Okay? And notice that if you have 2 poles, then basically you're dividing 2 into here, so it'll be 2 pi f, which is simply the radian frequency of the input AC waveform, right? So it'll be 2 pi times 60 hertz would be your synchronous speed. So the actual electrical radian frequency of the AC coming in would be equal numerically to the speed of the magnetic field that's rotating here if you have a 2-pole machine. Now if you have a 4-pole machine, then what's going to happen is you can see it's going to be what, 1/2 of that, okay? And so this is going to go 1/2 the speed of what's happening here. And if you have a 6-pole, okay, then that's going to be what, 1/3 the speed of what this is here, okay? And so you're going in, and the more poles you have, the slower the actual rotor is going, because your synchronous speed is going to get slower, okay? Now sometimes what you'll see is you'll see N instead of omega here, and N is in RPMs. And so if you want to know the synchronous speed in RPMs, then you multiply 120 times the frequency, which is 60, and divide by the poles, okay? And so this would be in RPM. So for instance, if the number of poles is 2, then you'd have 2 to 4 would be 2, so it'd be 2 pi times 60 would be the radians per second. And here what you would have is you'd have 60 times 60, okay, which would be 3,600, okay, for a 2-pole motor. Now here we come to what's called the slip, okay, and by slip here what we mean is we're accounting for the difference between the rotor speed, or the mechanical shaft speed, and the magnetic field that's rotating here. And remember, the rotor is trying to catch up to it, but it's slipping. It's never catching up with it. And so this slip is defined by the synchronous speed minus the actual speed of the shaft, the motor speed here, divided by the synchronous speed. R, in terms of RPM, it'd be the number of RPMs of the synchronous speed minus the number of RPMs of the motor shaft divided by the synchronous speed in RPM. Now here I'm doing R for rotor and S for stator, so this is stator, and that's what I've done here. That's not the slip here. Okay, so that's the basis of slip, okay, is just remember the rotor's always going slightly slower than the actual magnetic field that's pulling it, okay? Alright, let's go in and let's look at a model. Okay, so let me bring this up and let me get a zoom in here. Okay, so here's the model that we're using for the induction motor. Now notice what we've got is we've got some resistors here and some inductors. So let's go through and see what's happening. Okay, first off, let's start over here. So this is the voltage that is applied to the stator. This is like from the AC means, this is the 60 hertz sine wave or cosine wave that's being applied to the motor. And we're talking about 3-phase motors here. So essentially there's going to be 3 of these, 3 phases, and all 3 phases are 120 degrees out of phase with each other, which is your standard 3-phase power. Okay, so this is the model for 1 phase. Okay, now we'll go and look at something that will help bring this together a little bit better, but first let's look at the model components here. Okay, the first thing we have is we have the stator resistance. Okay, so this is the resistance of the coils that make up the stator. We have the magnetizing inductance for the stator coils. Okay, so this is the inductance that produces the flux that rotates, the magnetic field that rotates inside the motor, okay, between the stator coils and the rotor surface. Okay, now not all of that magnetic flux that's generated by this inductance actually goes in and links with the rotor. Some of it is lost, it leaks out. Okay, and so that is represented by LS, which is the leakage inductance or leakage flux for the stator. Now, this magnetic field or flux that's generated by the magnetizing inductance, or the coils that are in the stator, couples with the rotor. Okay, and when it couples with the rotor, it induces currents and voltages and a magnetic field inside the rotor. And the magnetic field generated by the rotor interacts with the magnetic field here. Now, not all of that magnetic field goes and interacts with this. Some of it is lost or leaks out, and that's represented by LR here. Okay, now R over S. This right here, this resistance, the current going through here squared times this, represents the power that's transferred from the stator to the rotor. Okay, now remember, the rotor has no direct connections to any power or anything. Okay, it's just some shorted turns that basically have the magnetic field induces current and voltage inside of the core. The rotor. And this right here represents the amount of power that's actually transferred to that. Now, some of that power is lost by the resistance in the conducting bars inside the squirrel cage, but the rest of it is actually gone in and turned into mechanical energy. The rotating shaft rotates the shaft of the motor, and some of it overcomes losses due to bearing friction and also to windage type losses. Okay, but for the most part, you're using this represents the power that's actually going to rotate the shaft. Now notice that this is broken down into two parts, and this equation here shows how that comes about. But you have RR, which represents the I squared R losses inside the rotor, and then you have RR times 1 minus the slip over S, and this represents the mechanical power. So IR squared times this represents the power that's gone to overcome any friction and to rotate the shaft. Okay, let's go in and look some more at some of these values here. So that this is the resistance of the stator winding, the leakage inductance of the stator, the magnetizing inductance of the stator, leakage inductance of the rotor. And let me be a little bit clearer here. This right here is what the stator sees through the magnetic field. Okay, and remember, the rotor interacts with the stator through the magnetic field. So things that are happening inside the rotor basically cause disturbances in the magnetic field, which result in these two components here. Okay, so these are components reflected. If you're thinking of a transformer, these are reflected into the stator circuit. Okay, and so the leakage inductance of the rotor seen by the stator, the resistance of the rotor seen by the stator, and then here is the total resistance seen by the stator as a function of RR and slip. And here the current in the stator and the current in the stator reflected from the rotor. So let's talk a little bit more about these up here. Okay, so here is the current that's flowing in the stator. Okay, of course, and this current is always also part of the stator, but this is current that's caused by things happening with the rotor. Okay, now let's look at some situations here. Now S equals 0 corresponds to the case where there's no slip, where your rotor is traveling at the same speed as the stator. Now, we've already said, or I've already said, that basically that can't happen, you know, that the rotor has no source of external power. It's getting its power from the magnetic field being produced by the stator coils. So it has to go slower than that. It's pulling it along. So S equals 0 would correspond to synchronous speed, and look what happens. You're taking RR and you're dividing it by 0, so this would be infinite, right? So at synchronous speed, if it were able to get that speed, then what you would have is a very large resistance here, very, very large, and so that means that this would be open. There would be no current flowing through here, okay? So under that situation there, actually all you have is the current flowing through RS, LS, and LM, okay? So predominantly an inductive type current is flowing through here, right? Seem more inductive, or the current, as they say, what Eli the Iceman, voltage leads current in an inductive circuit. Well, this would be mostly inductive, so the current would be lagging the voltage here because it's mostly inductive, and this would be 0. Now let's look at the other extreme case. The other extreme case would be S equals 1. So this would be the situation where what you have is a locked rotor, or a rotor that is just getting started, okay? In that case, S would be 1, and then R, it would just be RR, which is a very small resistance. In the situation we're going to be dealing with in this video are actual parameters taken from a 10 horsepower 220 volt motor, and the parameters, model parameters for that is, I believe this RR was like 0.144 ohms, okay, and this resistance here was like 0.294 or something like that, okay. So if you're talking about a locked rotor or just starting up, then basically this is going to be a really small resistor, 0.144. This right here is going to be a really small resistor, and so you're going to have a lot of current flowing through here. And in fact, this larger inductance, this inductance is much larger usually than these two values here. You're going to have some current flowing through there, but you're going to have most of the current kind of flowing through here. So you're going to have IR and IS pretty close, okay? This is under locked rotor condition. So those were the two extreme conditions, okay? Synchronous speed, which can't happen, and then locked rotor, which does happen, and now it's not really locked, you know, but it's not moving, you know, when you first start it up. Now let's consider the operating condition. The operating condition is that the slip here is typically somewhere around maybe 1%, that's 0.01, to as high as maybe 0.06 maybe, or 7, somewhere around in there, okay? In this video here, the problem I'm using, basically the problem is a problem from the book Electric Machinery, from Fitzgerald and Kingsley and Cusco. They were using a slip of 0.02 or 2%. Okay, so let's look at that. At slips that are really small, that are close to the synchronous speed. For 0.02, this right here is going to be around 7.2 ohms. Okay, and so here you're not going to have as much current as you had when the slip was 1. But it's going to be more than it was if the slip was 0, because remember, if the slip was 0, this would be infinite and you'd have no current, okay? And it turns out that the optimal power transfer is going to be somewhere around the slip equals maybe 0.2 as opposed to 0.02. So we're nowhere near the optimal output power here. But the operating condition is always somewhere around, say, 0.01 to 0.07 or 8, somewhere around in there. Okay? Okay, so let's continue on. And so here's some more stuff on slip that we talked about. Here is the same thing we already talked before here. Let's look at this right here. So for 60 hertz AC line coming in, if you have 2 poles, then you're talking about 3600. Okay. If you have 4 poles, you're talking about 1800 RPMs, and so it's about half of that, like I said before. And if you had 6 poles, then that's going to be like 1/3 of that, or 1200. And if you have 8 poles, it'll be 1/4 the speed. So more poles means a slower angular velocity. Now, here's the thing, is the actual motor speed is going to be some percentage of this. So if you have a slip of, say, 0.2, then that means, not 0.2, a slip of 0.02, then that means that you're going to have a speed here that's going to be 1 minus 0.02, or 0.98 times that. Okay? And if you're talking about a slip of 4%, then you'd have a speed of 1 minus 0.04, which would be 96% of this. So you're always going to be some percentage of this depending on the slip. Okay? All right. Now, time's kind of gone by here. Before we go, I'd like to show you a couple other things. So let's go and go back to here. And let me show you some models. So this here is the model that we are using, and notice we have some values here. Now this is phase A, phase B, phase C. What we saw was the model just for one phase, and so when we go and calculate things like torque and power and things like that, then we're going to have to multiply those by 3 to get the actual value for the whole motor. Line current is going to be what we calculate it to be. What we're doing in the example we're doing is basically it's a 10 horsepower, 220 volt line-to-line 3-phase motor, induction motor. And so what that corresponds to, if you take the 220 volts, which is line-to-line, and you divide it by the square root of 3, then you'll get 127. Okay, so it's 127 volts RMS across here, 220 volts RMS across here, and again they're related by the square root of 3. So 220 across here to here, or here to here, or here to there, and this is about 127. Now this shows up 180 because the peak voltage will be the square root of 2 times that, which is 180. Now notice the values that we're using here. We got 0.294 is for the equivalent resistance for the stator in each winding. We got 0.144 ohms for the losses incurred inside the rotor, and then this is for this 7.056 is the value for a slip of 0.02. Okay, and then this is the magnetizing inductance. This is the leakage due to the rotor. This is the leakage due to the stator. Okay, and so here the 3 phases coming into the motor. I really don't need this here, but I tied it here to here. And as long as these currents are balanced, then the net current here is going to be 0. So it doesn't really matter if I put anything here because no current is going to flow through here. And maybe we'll look at that a little bit later. Also, what I have is I have the model for just one phase, and we'll probably be spending more time looking at this than we will the other. But anyway, so this is how we're modeling. So we're going to be looking at here, but we're also going to be looking at what's happening using Python. Okay. So anyway, let's see. Is there anything else I want to show here? Time is going really fast here. I think not. I think now is a good time to take a break. And so in the next videos, we'll go in and actually do some calculations and do some plots. All right, we'll see you in the next video.